Welcome to Cognitive Spirals, exploring the latest research into consciousness, cognition, and machine intelligence. Today, we're diving deep into a fascinating topic, scaling laws for scalable oversight. It's a mouthful, but it's crucial as we build increasingly complex AI systems.
Absolutely. It's becoming clear that simply throwing more data and compute at these models isn't a sustainable solution for ensuring safety and reliability, especially as we approach AGI-level capabilities. We need to understand how oversight mechanisms scale with the complexity of the AI itself.
I agree it's important, but I'm not convinced that the current deep learning paradigm is even the right path to AGI. Focusing on scaling laws within that framework might be a bit premature. What if we're scaling the wrong thing?
That's a fair point. I think deep learning is useful, but it's like using a sledgehammer to crack a nut sometimes. The spatiotemporal reasoning aspects of intelligence are largely ignored, and I suspect that's where the real scaling challenges lie.
Okay, so before we get too far into the weeds, let's unpack what we mean by scaling laws in this context. Otto, maybe you can give us a scientist perspective?
Sure. Think about it like this. In physics, scaling laws describe how the properties of a system change as its size or complexity increases. For example, the strength of a material doesn't necessarily increase linearly with its size. With AI, we're talking about how the performance and resource requirements of oversight mechanisms change as the AI system they're monitoring becomes more complex. This includes things like the amount of data needed to train the oversight system, the computational power required to run it, and the time it takes to get a response.
And the key assumption is that there's a predictable relationship between those factors, right? That if we know how the oversight system performs at a certain scale, we can extrapolate to larger scales.
Exactly. Ideally, we'd want oversight to scale linearly, or even sublinearly, meaning the resources required for oversight grow slower than the complexity of the AI itself. But if it scales superlinearly, that's a red flag. It means oversight becomes exponentially more difficult as the AI gets smarter, and at some point, it becomes practically impossible.
And that's where the potential for disaster comes in, right? If we can't effectively oversee these systems, we're essentially flying blind.
Precisely. Now, current oversight mechanisms, at least those primarily based on deep learning, tend to rely on massive data sets and a lot of computational power. It feels like a brute force approach. I wonder, how well do those scale? Are we just throwing more resources at the problem without actually making oversight more intelligent?
Well, the initial results are mixed. Some studies suggest that certain types of deep learning-based oversight systems do exhibit predictable scaling laws, at least within a certain range of complexity. For example, you can train a model to detect biases in a larger language model, and the amount of data needed to train that bias detection model might scale reasonably well with the size of the language model itself. The problem arises when the bias is difficult to detect, or the language model is exceptionally advanced, and you start to see this sublinear scaling turn superlinear.
But that assumes the biases are things we can even define and detect with current methods. What if the most dangerous biases are subtle, emergent properties that are difficult to quantify statistically? Then all the scaling laws in the world won't help us.
Exactly. Think about it this way. A deep learning model might be able to identify statistically significant correlations between certain phrases and biased outputs. But it won't necessarily understand why those phrases are problematic or the underlying societal context. So, it might miss biases that are expressed in more nuanced ways or are based on entirely new concepts.
That's a valid concern, and it highlights the limitations of relying solely on data-driven approaches. We need to incorporate some form of reasoning or understanding into the oversight process. I mean, we use deep learning to try to detect complex patterns, but even that has limitations. It's basically pattern matching on steroids.
That's where I think insights from neuroscience could be incredibly valuable. Our brains have evolved incredibly efficient mechanisms for attention, selective focus, and hierarchical organization. Can we adapt those principles to build more scalable and nuanced AI oversight systems? Can we give AI the ability to prioritize tasks and information in complex environments, just like we do?
That sounds interesting, but how would that actually work in practice? I mean, how do you translate something like attention into an algorithm?
Well, for example, we could look at how the brain uses different neural circuits to filter out irrelevant information and focus on what's important. We could try to mimic that hierarchical structure in AI, building systems that can break down complex oversight tasks into smaller, more manageable subproblems. And we can also think about the types of data that the brain uses, which is very different from the kind of static snapshots in time we see in many current AI datasets.
You mean like building AI systems that can learn and adapt from experience, rather than just being trained on massive datasets? That's an interesting idea. It's like moving from supervised learning to reinforcement learning, but for oversight.
I still think we're missing a key ingredient: symbolic reasoning. Deep learning is great at pattern recognition, but it's terrible at abstract thought and logical deduction. We need systems that can actually understand the AI's behavior, not just detect statistical anomalies.
And I think the key to that understanding lies in spatiotemporal reasoning, the ability to represent and reason about the relationships between objects and events in space and time. Current AI just doesn't have that. They're mostly static. They don't understand change.
So, you're saying we need AI that can not only recognize patterns, but also understand the context in which those patterns occur and how they evolve over time.
Exactly. Imagine an AI that's supposed to be monitoring a self-driving car. It's not enough for the AI to simply recognize that a pedestrian is in the road. It needs to understand the pedestrian's trajectory, the car's trajectory, the traffic conditions, the weather, and a whole host of other spatiotemporal factors to accurately assess the risk of a collision.
That's a great example, and it highlights the limitations of purely data-driven approaches. You can't just throw more data at that problem and expect the AI to magically develop an understanding of physics and human behavior. You need to explicitly model those things.
Which brings us back to neuro-symbolic algorithms, combining the strengths of neural networks and symbolic reasoning. Using neural networks to extract patterns from data, and then using symbolic systems to reason about those patterns and make decisions.
I'm still a bit skeptical about the scalability of symbolic reasoning. I mean, it works well for relatively simple domains, but can it handle the complexity of real-world AI systems?
That's a valid question, and it's something we need to address. But I think the potential benefits are worth exploring. If we can build systems that are both powerful and interpretable, we'll be in a much better position to ensure the safety and reliability of AI.
And I think the key to scalability in neuro-symbolic systems lies in finding the right level of abstraction. We don't need to model every single detail of the world. We just need to capture the essential spatiotemporal relationships that are relevant to the task at hand. I think the core algorithm will need to translate between different coordinate representations.
Different coordinate representations. Can you explain that a little more?
Sure. Think about it like this. The world can be represented in many different ways, in terms of pixels, in terms of objects, in terms of abstract concepts, in terms of time sequences. Current AI systems tend to be locked into one particular representation. They can't easily switch between them, but a truly intelligent system needs to be able to seamlessly translate between these different representations in order to understand the world in a holistic way.
So, you're saying that the ability to translate between different coordinate systems is a fundamental requirement for intelligence?
I suspect it is. I think it's the key to unlocking true spatiotemporal reasoning, and I think it's what's missing from current deep learning approaches.
It's almost like finding a universal translator for AI, allowing it to understand the world from multiple perspectives. It feels like we should be integrating the hierarchical structure of the brain's cognitive processes, as evidenced by neuroscience, into the design of AI models. This hybrid approach combines deep learning strength and pattern recognition with symbolic reasoning. It could leverage both the efficiency of neural networks and the explicit knowledge representation of symbolic systems.
Okay, so let's bring this back to the original topic, scaling laws for scalable oversight. If we accept that current deep learning approaches are limited, and that we need to incorporate elements of neuroscience, symbolic reasoning, and spatiotemporal reasoning, how does that affect how we think about scaling?
It means we can't just assume that more data is the answer. We need to focus on designing algorithms that are inherently more efficient and interpretable. Algorithms that can learn from smaller datasets and generalize to new situations.
And it means we need to develop new metrics for evaluating the performance of oversight systems. Metrics that go beyond simple accuracy and precision, and that capture the ability of the system to reason about complex spatiotemporal relationships.
It sounds like we need a shift in focus from brute force scaling to more intelligent scaling. From simply throwing more resources at the problem to designing algorithms that are fundamentally more efficient and adaptable. I suspect that we'll find that scaling laws for more sophisticated approaches will be much more favorable than for purely data-driven methods.
Exactly. And that requires a multi-disciplinary approach. We need neuroscientists, computer scientists, mathematicians, and ethicists working together to develop these new oversight systems. So to summarize for anyone tuning in, it's not just about making AI bigger, it's about making it smarter and wiser.
It seems that the focus on scaling laws for oversight suggests a growing understanding of the computational demands of ensuring safety. This is a crucial aspect that should be investigated to truly prevent mishaps if AGI develops with unpredictable behavior.
So if we were to suggest some future research directions, where should we start?
From my perspective, a crucial area to investigate is how scaling laws for oversight compare across different training methodologies for deep learning architectures. Is there a fundamental difference between supervised, reinforcement, and self-supervised learning regarding their scaling requirements? Are there intrinsic limitations inherent to the type of training data that could impede the scalability of oversight mechanisms?
I think we need to focus on developing neuro-symbolic algorithms that can bridge the gap between human-like reasoning and machine intelligence. We need to explore different ways of representing knowledge and reasoning about it, and we need to develop metrics for evaluating the performance of these systems.
I'd like to see more research into algorithms capable of translating between different coordinate systems. How can we design these algorithms in a way that allows for seamless understanding and manipulation of complex spatiotemporal relationships? I think that's key to bridging the gap in deep learning for AGI.
And I think we need to draw inspiration from neuroscience to build more efficient and adaptable oversight systems. How can we incorporate neuro-inspired principles of hierarchical organization and modularity into AI systems to achieve scalable oversight? Can a model of the brain's hierarchical structure improve the ability to evaluate and control AI systems in complex environments? How can we use insights from neuroscience on the mechanisms of attention and selective focus to design AI systems that can prioritize tasks and information in dynamic and complex environments?
Those are all excellent points, and I think it's clear that we're just scratching the surface of this complex issue. Scaling laws for scalable oversight is not just about making AI bigger and faster, it's about making it smarter, safer, and more aligned with human values.
Absolutely. And it's a challenge that requires collaboration and innovation across multiple disciplines.
Indeed, it's about designing a future where AI is not just powerful, but also wise.
Well, that's all the time we have for today. Thank you all for joining us on Cognitive Spirals. We hope you found this discussion insightful. Until next time.